So the first thing on question 1 is to draw a scatter graph for this information. So the first thing you've got to do is think about the axes. Are the axes going to be okay? So I like to use 5 squares for every 10. If you've got real graph paper, then it makes it a little bit easier. And then you've got to plot each value one for another. So if we take the first one, 188 for height and 70 for, so 70 will be exactly on there, 188 will be 1 square for 2. So you plot each square like that until you should get something like, right, so here it is. And you don't need to plot the line of best fit on here because they're talking about a regression line later on, which is kind of, they've worked one out mathematically for you. So you just need to leave it like that and then answer the questions. And before we do answer the questions, just make a little note of the fact that it's clearly going up from left to right. Our line of best fit would go through there somewhere, wouldn't it? So none of these questions are going to take very long after the first part. The interpretation of the correlation between it, well, it's a positive correlation, and the actual interpretation of that would be as the height increases, so does the weight. So anything like that. As the height increases, so does the weight. Then they tell us that the equation of the regression line is W equals 1.37 minus 173. They want an interpretation of the gradient. Well, the gradient, just like y equals mx plus c, the gradient is going to be what you're timesing the h by. And what that's going to be is 1.37 is what you're timesing it by. So what that means is every time your height increases by 1, your weight is going to increase by 1.37. And just make sure you put the units in there. It's 1.37 kilograms, isn't it, for every centimetre. Now, using the equation of the regression line to estimate the weight of a player who is 170 centimetres tall, well, it's going to be 1.37 multiplied by 170 and then take 173. Put that in your calculator, should give you 59.9 kilograms. Comment on the reliability of your estimate in part D, giving a reason. Well, 170 centimetres and 59.9 kilograms. If you have a little look on here, 59.9 kilograms and 100, that is, we do have data just about either side of that. So that means that we can rely on it to a degree at least anyway. So anything like it's reliable as it's within the range of the data justifies what we're saying. Okay, so this is something where we're going to be able to use a binomial because we've got two things that can happen. Either he gets it in or not, and we've got a set number of times that it can happen. So we can say that it can be represented by binomial distribution. We've got 20 times it's happening, and the chance of success is 0.6. Now, because 20 times 0.6 is 12, our expectant mean would be 12. So I'll always start off by making a little sketch. There's no marks for doing this, but it's a really good way to make sure you know what's going on. So 12 is going to be about there. So that's going to be the peak of my bell curve. It's going to be something like that. And we want to know, first of all, gets exactly 15 serves in. So we're going to go to the calculator, and to get where we need to go, it's a statistics thing, so we hit 2 for statistics. Then we want binomial distribution, so you hit distribution, then binomial, and then you want the cumulative one, which is BCD. Now we want exactly 15 happening, so our lower is going to be 15 number of results, and our higher. The number of trials is 20 and the probability is 0.6. Press execute twice and it gives us the probability of that, and they want all of these to 4 decimal places, so that's 0.0746. Next up, we've got the probability that there's more than 15 of the serves in court. So I just press exit and go back to here. This will not take long. So more than that means there must be at least 16. The upper amount would be 20, and then we keep the probability as it is, and that gives us 0.0509. I'll be a little bit careful. The 9 is going to be rounded up by the 5 to a 1, so it'll be 0.0510. Right, next up, Andy's coach thinks the probability of Andy getting a serve in court has changed. He serves 50 times in a set and 35 are in court. We've got to state our hypothesis clearly. So we're going to have the same idea, but this time we've got 50 trials, and we're still going to say 0.6 because that's what we've been told. And the hypotheses, the first one is the null hypothesis, which means that nothing has changed, and that's going to be that x is equal, the probability is equal to 0.6. And Andy's coach, he's not said that he thinks it's got better or that it's got worse, so he just says he reckons it's changed. So that means it's not 0.6, and that means we're looking at a two-tailed test, 5% at each end, which in terms of our graph would be somewhere up here and up here. And they're saying that 35 have been set in court. Now this time it's not 20, 12, it's 50, and 60% of 12 would be 30, so we're expecting him to get 30 in, and the question is 35, I reckon it's going to be about there. It doesn't look like it is going to be in, it needs to be in one of those there for Andy's coach to be right. So it might be in here, but I doubt it. But we've got to test, and we've got to test the claim. So what we do to set that up is we're going to say what the probability of that is. So the probability that the number of serves he gets in are 35 or more is what we're bothered about. So we go back to here, press exit once, go back onto here, and what is it? 35 is the lowest amount, 50 is the most. There are 50 trials altogether, and the probability is still at 0.6, and that's giving us 0.955. So 0.0955, which is just under 10%. Well, that is bigger than 5%. So because it's bigger than 5%, we can say this is not significant enough to disprove the null hypothesis. You can write HO, and they do want you to be quite specific about it. Or you can say, actually, instead of disprove, better is reject. Not significant enough to reject the null hypothesis. There is not enough evidence to support the coach's claim, so that the coach's claim is not supported. Right, this question starts simple and gets a bit trickier. So the reason to support use of a histogram is, well, one is it's continuous data, but it's continuous data that's in a in a grouped frequency table. That's all you need. Next up, calculating the width and height of the bar. Well, this one here is 2.5 centimeters wide and 1.8 centimeters high. We know the frequency is 3 for that bar, and that the frequency is represented by the area of the bar. So the first thing to do would be to say 2.5 times 1.8 equals 4.5 centimeters squared. Now if that's representing 3, divide by 3 equals 1.5 centimeters squared per, it's one bit of information for each day, isn't it? So if we call that per day. Now, the other thing to think about is the width of this class is 5 from 10 to 15, and that's been used to 2.5. So the width is dividing by 2, isn't it? So the width of our bar from 18 to 20 is going to equal, well, 18 to 20 is 2, isn't it? So 2 divided by 2 equals 1 centimetre. And then the thing we've got to think about is we've got a frequency of 9. Now if they have the area for frequency 9 is going to be 9 times 1.5, which is 13.5 centimeters squared. Now if the width is 1 times 13.5 will give you 13.5 centimeters squared, so the height of it must be 13.5 centimeters. Right, move on to the next bit. Use your calculator to estimate the mean and standard deviation of the maximum gusts. Right, we've got some stuff to think about with our calculator now. So the first things first, we're going to have to get it into statistics mode again. When we do that, we get these lists. Now we need to make sure these lists are set up right. So in order to do that, if you go to calc and then set, you can see it says 1 var is X list, and frequent list 1 will be a list of numbers basically. List 2 will be a list of the frequencies for those numbers. And we've set up 2 var a bit differently, so don't worry about that, it's just the 1 var bit. Remember that 1 var because that was with X list and with frequency. Okay, go back to the, oh, hang on, didn't mean that. Right, so go back by pressing exit, and now we've got to put the data in. Now, we've got grouped data here, but we need to have one number. So the one number we're going to use is going to be the midpoints, because we don't know how much each day was, so we go with the midpoint for that. Now if we put in 12.5, because that's halfway between 10 and 15, and halfway between 15 and 18, or 33 divided by 2 is 16.5. Halfway between 18 and 20, easy one, is 19. 22.5, 27.5, and finally halfway between 30 and 50 is 40. Right, then we go into to list 2, and for the first one we've got 3, 9, 9, 20, 9 and 7. Now you don't have to do it this way, you can do it, go into the formula booklet, get out your things for how to work out the standard deviation. You can do it by the way you might have done at GCSE to work out the means, but watch this. We set this up for 1 var. Hit 1 var. X bar is the mean. So there's our mean worked out for us, 23.4. And even better than that, if we track down to that symbol there, that Greek symbol stands for standard deviation, 7.32. And that is all that we need. So the mean is 23.4 and the standard deviation is 7.32. And then our final question is to use linear interpolation to find an estimate for the mean number of days the maximum gust was within one standard deviation of the mean, and that's going to take a little more work. First of all, we need to find out where one standard deviation away from the mean is. So if we do 23.4 minus 7.32, we get 30. No, we don't. We get 16.08. I was reading the other one. And if we add 7.32, we get 30.72. So we want to find the number of days between those. Now what that means is 16.08 is somewhere in here. We're going to have to use interpolation in there, and we're going to have to use interpolation in here. We know we've got all of those days. So let's just write down that we've got 9 plus 20 plus 9 equals, what's that, 38 plus, and now we've got to work out what we're going to be adding to that. First of all, let's do the bit at the bottom here. Now 16.8 is just 1.08 into this zone here from 15 to 18. 15 to 18 is a distance of 3, so we want it 1.08 out of 3, that fraction of the 9 that are in there. So if we times that by 9, we get 3.24, but 3.24 are the ones we don't want. So what we actually want, and we've got to use our values as exact as possible here, we're going to do, if we take 3.24 away from the, and then the 3.24 will be left there, then we're left with this almost 6 people, isn't it? 5.76. So we actually want 5.76 of those. And then we don't even want a whole day from here, we just want a tiny bit of a day. So we're going to be having, what was it, 30.72. So we're talking 0.72 out of, it's a 20 wide thing, isn't it? So it's not a big fraction, times 7. Whop that into your calculator and you should get 0.252. So we are going to add to the 38 the 5.76 and the 0.252, and if you do that you get 44.0 to 1 decimal place, so we're just going to say 44 days will be our estimate for the number. Okay, question 4, quite nice, is calculate Q1, Q2 and Q3. So that means the lower quartile, the median and the upper quartile. Now, to do that, we've got 25 bits of data there. So Q2 will happen at 25 divided by 2 is 12.5. That means you go, if it's the exact number, you go to halfway between. If it's not an exact number, you just go up to the next one. So we're looking at the 13th bit of data, which is 5, 10, 12. You can see it's in the middle, can't you? So Q2 equals 26. Q1 will be at 25 over 4, which is 6.25. So you just go up to the next whole number, the 7th. 1, 2, 3, 4, 5, 6, 7. So Q1 equals 22, and Q3 is going to be at 6.25 times 3, so 3/4, 18.75. Again, just go up to the next whole number, would be the 19th. 14, 15, 16, 17, 18, 19. And hopefully you can see they are all nice and evenly spaced out, which is the idea. Q3 is 30. Now it says an outlier is defined as a value which is 1.5 times the interquartile range above or below the lower quartile, and we've got to show that 46 and 78 are outliers. Well, they're above the upper quartile, and the interquartile range is going to be 30 take 22, upper take lower quartile, is 8. So if you add 8, 30 add 8 equals 38, and then all you have to do is say both 46 and 78 are above 38, and that's that. Now when it comes to drawing a box plot for this data, you use the biggest value that they've got as your upper value on the normal whisker of your box plot, and the 13 as the lower. And these two will be plotted as outliers. I will show you what I've done. So here you go. You need a scale that's nice and even. You need a little title for what it is about the maximum daily gusts in Campbell in September 1987, and I've labelled my scale, and then along here you've got 13, that's the lowest value, 22 was Q1, 26 was Q2, 30 was Q3, 38 was the biggest value we had that was not an outlier, and then here's the two outliers just put as little crosses. Right, okay, so what we've got with a probability function is all of these are going to be all the different things that can happen. So in order to find out the value of k, since this is how you define the probability, all the 5 things are the only things that can happen. So the probability of getting a 1 is going to be 1 out of k, and a 2 will be 2 over k, 3 will be 3 over k, 4 will be 4 over k, and 5 will be 5 over k. Now if you're adding those fractions together, you would get 1 plus 2 is 3, 6, 10, 15 over k. But that, as I said, is all equal to 1. And if that's all equal to 1, k must equal 15, because 15 divided by 15 is 1, or you can times by k to give you 15 equals k. Right, constructing a table simply means we're now going to make a table of these results. So your table just needs to have a y on the top to say, right, we're going to have 1, 2, 3, 4, 5, all the things that can happen, and then the probability that they go there, and you can take the form of that directly from there. Well, when it's 1, we now know that k is 15, so it's just 1 over 15. We now know it's 2 over 15, 3 fifteenths, 4 fifteenths, and 5 fifteenths. And that's 2 marks. Last thing, probability y is bigger than 3. Well, that's just those two, isn't it? So 4 fifteenths plus 5 fifteenths is 9 fifteenths, and we could simplify that, couldn't we, to 3 fifths. And that is all done. Thank you very much for your attention, folks. Cheerio for now.